Welcome back. In the second part of our lecture, we're going to talk about the second measure of relative standing called a z-score. So first we want to try to understand what a z-score is, and I think you'll find it's quite simple. We've been talking about how the mean is considered to be the center of a data set when it's symmetric. And we're going to actually take that idea and extend it a little bit further and start thinking about the mean as, say, the origin of a coordinate system. Now, we said we could think of the standard deviation as a measure of the width of a data set. And we're, again, going to take that notion and extend it a little bit. And we're going to start thinking of the standard deviation as a unit of measurement, or like a unit of distance. So you know how in the military you have a click, and it means, 1 kilometer. You could talk about 2 clicks. That means 2 kilometers. Well, we're going to think about the standard deviation as a click. It's going to be, a unit of length. And so I'm going to start thinking of the mean as my home base, and I'm going to start measuring off distances from the mean in units of standard deviation. So 1 standard deviation above would be plus 1 click, and so on. And also, I'm going to consider the values below the mean, again, in units of 1 standard deviation. And so the z-score is going to be another measure of relative standing. It's going to tell me where I am in those values in a particular distribution. Specifically, it's going to tell us the number of standard deviations a data value is above or below the mean. And so we're going to compute the z-score of a data value by subtracting its value from the mean and dividing by the standard deviation. And so we can think of the z-score as telling us how many clicks above or below the mean a particular data value is. And so if you think about it, these red values would be z-scores. This is 1 standard deviation above the mean, so it's going to be plus 1. Okay, so let's get a little practice with computing z-scores as the number of standard deviations of data value is from the mean. So if we look at IQ, we've been talking about how IQ has a normal distribution, and it's known actually to have a mean of 100 and a standard deviation of 15. So you could ask the question, what is the z-score of the data value 70? And I'm going to use my formula. And actually, if you look at this plot, you can see what the answer is, right? This is 1 click below, 2 clicks below. So we know the z-score is going to be minus 2. But let's also use our formula, because there will be times when it's not a nice number of standard deviations. So our formula says, okay, take the data value, subtract it from the mean, and divide by the standard deviation. And sure enough, when we do, as advertised, we get negative 2. What about the z-score of 100? Well, we're already at home base, right? Where the mean is the origin. So if someone were to say, how do you get from home base? If you're standing at the home base, you tell them go 0 clicks, right? And again, if we employ the formula, sure enough, we see 0. So the mean has a z-score of 0. Data values that are above the mean have positive z-scores, and data values that are below the mean have negative z-scores. What if we want to go backwards? What if I tell you the z-score and I say, what is a data value that has that z-score? So what data value has a z-score of positive 2? Well, again, you can see it from this picture, right? Z-score of positive 2 means it's 2 clicks above. So this is 1 click, because a click is 15 here. This is 2 clicks, so it's 130. But let's puzzle through it with our formula. So our data value, we're going to start at the mean, and then we're going to go the number of clicks that our z-score tells us to go. So the z-score here tells us to go 2 clicks or 2 standard deviations, which is 30. What if we have a data value that has a z-score of minus 3? Well, we know that z-score, that data value is going to be below 100 because it has a negative z-score, And again, if we start off at home base, start off at our origin 100, and we go 3 clicks below, we end up with a data value of 55. So let's go ahead and look at this particular reading quiz problem. This is actually reading quiz problem number 4. Just ignore the 2. I'll take that out in your version. And suppose we are part of a marketing team at an internet music store. We want to get to know our customers better, so we send out a survey and collect demographic information on them. And obviously, a really important variable when we're talking about musical tastes is the customer's age. And so if you click on this particular link here, it will take you to a Google spreadsheet that has the age of 25 customers who responded to the survey. And what we want to do is we want to standardize the maximum and minimum ages in our data set. Now, standardize is code word for compute the z-score. And we'll talk later on about where that standardized term comes from. But what I want to do is I want to take the minimum and maximum ages and take the mean of that data set, which is 32.8, and the standard deviation, which is 9.429. And I want to compute the z-score for the minimum age and the z-score for the maximum age. So go ahead, stop the video. You can go ahead and open up StatCrunch to import this data set, sort them, find the minimum and maximum ages, and then using this mean and standard deviation, go ahead and compute the z-scores of the minimum and maximum age. So how do we use z-scores? Well, we're going to use z-scores to compute probabilities. And we already know that if we have the percentile of a data value, it actually gives us a probability. But how can we do that with a z-score? And the answer is it depends on the data that we're looking at. So for example, if we're looking at an actual data set and it's symmetric and mound shaped, we're going to use something called the empirical law or the empirical rule. However, if we're working with a population, say from a normal distribution, we're going to see how we can use StatCrunch to compute those values. And we've used StatCrunch a little bit already. So let's go ahead and see how to compute probabilities using the empirical law. So the empirical rule is sometimes called the 68, 95, 99.7% rule. And what it says is, if you have a data set that is symmetric and mound shaped, in other words, unimodal symmetric, and so I'm looking here at the sample mean, not the population. That's why I have X bar, and I have S for the sample standard deviation as opposed to sigma. The empirical rule tells us that if we look at the data values that are 1 standard deviation from the sample mean, that's going to be roughly 68% of our data set. So roughly 68% of our data set has values that are within 1 standard deviation of the mean. And now you can kind of guess where the 95% comes from, right? If we look 2 standard deviations from the mean, we're going to find that roughly 95% of the values are in that range. And finally, if we look 3 standard deviations from the mean, we're going to find that practically all of the data set is within that range. 99.7% of the data values are within 3 standard deviations of the mean. That's a really useful fact. So let's go ahead, and you can see also, I'll just mention before we leave this slide, I can also cast this in terms of z-scores. Okay? The percentage of data values that have z-scores between -1 and +1, which is the same as saying the percentage of data values that are 1 standard deviation above and below, is roughly 68%. So let's go ahead and look at situation where we had the distribution for the prices of new Honda Accords. We know it's going to be symmetric and mound-shaped. And let's just suppose from the data we find out the mean is 29,500 and the standard deviation is 3,500. A really good rule of thumb is when you're going ahead and you're working problems like this to kind of sketch out the distribution, right? So I know that this distribution is going to be symmetric and mound-shaped. I'm going to go ahead, I'm going to enter the mean at the center. And then I'm going to step out in units of 3 standard deviations on both sides. Notice the standard deviation is kind of like a ruler, right? We're measuring things in units of standard deviation. And now let's ask some questions that we can answer with the empirical rule here. So suppose I want to know what is the likelihood that a randomly chosen car has a price less than 29,500. Well, again, we're going to go back to what we know about these curves, right? Probabilities or areas under the curve. The area under the whole curve is 100%. So 29,500 here is right at the center. Okay? So this is going to be half of 100% or 50%. And it's not surprising because we know that for symmetric data sets, the center is also the median, which is the 50th percentile. Let's ask the question that a randomly chosen car costs less than 22,500. Now, when we're working with the empirical rule, it's important to realize we don't actually care about the data value itself. All I care about is how many standard deviations above or below the mean my data value is. So in this case, 22,500 is 2 standard deviations below the mean. And what do I know about data values that are 2 standard deviations above and below? I know that 95% of the data values are in this range. Now, the area under the whole curve is 100%. So I notice that I can kind of break this curve up into 3 parts. This little tail here, this middle part that's 95%, and this little tail here. And the areas of these 3 regions have to add up to 100%. So if this middle region has an area of 95%, the area of these 2 tails to make everything add up to 100% has to be 5%. All right, and now I'm going to use symmetry. So I'm going to use the fact that these 2 tails have the same area. So if they have to add up to 5% and they're each going to be equal, they're each 2.5%. So this area here is going to be 2.5%. And that's the probability that I get a value less than 22,500. And we remember that percentiles answer the question how likely, and they're areas that are in tails. So what if we want to answer the question how likely it is that a randomly chosen Honda Accord costs more than 33,000? So again, I'm going to ask myself, how many standard deviations away from the mean is 33,000? Well, it's 1. And the empirical rule tells me that 1 standard deviation away from the mean is 68% of the values. And I'm going to do this, play the same game that I just did in problem B, right? I'm going to say everything under the curve is 100%. This middle part's 68%. So these 2 tails have to be 32%. And by symmetry, they have to have the same area. So I'm going to divide that 32% in half. And this upper tail, which tells me the probability I get a randomly chosen value more than 33%, is going to be 32% divided by 2, or 16%. Now we come to a hard problem. What if I want to find out how likely it is I'm going to randomly choose a value between 19,000 and 33,000? Now I look at this, and these data values are not the same distance away from the mean. 19,000 is 3 standard deviations, and 33,000 we just saw and part C is 1 standard deviation. But we're still going to use the empirical rule because we know that 3 standard deviations away is 99.7%, but this is half because it's half of that area. So it's going to be 99.7 divided by 2. And this is going to be 34% divided by 2. And so we can just do this on our calculator. It's going to be 49.85% from this lower tail plus 34% from this upper tail. So the total area under this curve is going to be 83.85%. And so this is how we use the empirical rule to compute probabilities. And what I would like you to do is go ahead and try the problem on the reading quiz here. So we know that a normal distribution is what we sometimes say a normal model for the data. And we're going to use the empirical rule in this case, even though we're working with physiological data. All we need to know is that it's mound-shaped and symmetric. So suppose we know that systolic blood pressure has a normal distribution, and the mean's 110 and the standard deviation is 8. And medical professionals are going to diagnose you as having hypertension or high blood pressure if your blood pressure is in the upper 2.5th percentile. And I'm going to use the empirical rule, not the normal distribution calculator. Using the empirical rule, I want to know what blood pressure is the threshold past which you are diagnosed with hypertension. And you're going to kind of work backwards now, okay? You're going to be given the upper 2.5th percentile, and you're going to kind of work backwards and use symmetry to figure out what that blood pressure is. So a good thing to do is to sketch out this distribution. Kind of make a nice bell-shaped curve, put the center at 110, and step out in units of standard deviation, 3 standard deviations above, 3 standard deviations below. And that really will help you solve a lot of these problems. Okay, so let's talk about how to compute probabilities for normal distributions using z-scores. And we've already talked about kind of the notation, right? We use mu for the population of a normal distribution. We use sigma for the population standard deviation of a normal distribution. And I'm going to introduce a new piece of notation. So when I write capital X is equal to n, and in the parenthesis I put mu and sigma, what this means is I'm looking at a variable x, and the equals n is read as has a normal distribution with mean mu and standard deviation sigma. And so if I were to draw that, it would look like this. And of course, we're generally going to enter numbers for the value of the mean and the value of the standard deviation. Now, we want to introduce a new concept here associated with the normal distribution and z-scores. We're going to kind of tie them together. And this is called a standard normal distribution. So the standard normal distribution is a specific normal distribution. It's a normal distribution whose mean is 0 and whose standard deviation is 1. And the reason why it's called standard is it lets us compare values from different normal distributions. Because it turns out that if you take any normal distribution and you compute its z-scores, they have a standard normal distribution. In other words, if I have some random variable x that has a normal distribution and I compute the z-scores, they always have a standard normal distribution. And we're going to see now how this standard normal distribution, these z-scores, let us compare values from any two normal distributions. So what I'm going to do is I'm going to consider SAT and ACT scores, and standardized test scores generally have normal distributions. So the SAT has a normal distribution. The mean is 500. The standard deviation is 100. See if you can practice saying this second statement here. ACT scores have a normal distribution. The mean is 18, and the standard deviation is 6. Now let's suppose we come back to our buddies Jack and Jill. Okay, they're still competing, trying to get into college, and they're competing for admission to a specific college. So Jack takes the SATs and he gets a score of 650, and Jill takes the ACTs and gets a score of 22. And we want to ask, based just on their test scores, who should the college admit? And let's suppose that they're equal in every other sense as far as their application. Obviously, they're not equal with respect to gender, but let's suppose the college is going to be gender blind. They're not going to weight one candidate over the other based on gender. So based solely on their test scores, who would get in? Well, here's the SAT score distribution, right? It's normal with a mean of 500, and we're stepping out in units of 100 here for the standard deviation. And this is Jack's SAT score of 650. And I know that if I took those SAT scores from that normal distribution and I computed the z-scores, it would have a standard normal distribution. And so the z-score that Jack has is 1.5. And since the z-scores from any normal distribution come from a standard normal, I can plot Jack's here. Now notice the ACT scores, again, have a normal distribution. Their mean is 18. I step out in units of standard deviation of 6. And again, we can't compare Jack and Jill's scores directly, right? I mean, a monkey could take the SAT and score higher than the brightest person taking the ACT, right? So what we're going to do is we're going to look at Jill's score, and we're going to play the same game. We're going to compute the z-score for her ACT score, which is 0.66. And we know that for this ACT distribution, if we compute the z-scores, they're also going to come from this same distribution. So now I can put Jill's score on here, and I can compare their test scores. So notice what standard means here. A standard normal means the same thing that the gold standard means, right? When we used to actually have a good economy in the US, we had the gold standard. And what it meant was that everything could be compared relative to the price of gold. Well, the same thing is true here. The standard normal lets us take values from any normal distribution and convert it into the standard normal so we can compare them. So now we can compare Jack and Jill's scores, and we can tell that Jack did better. He's more z-scores above, he's more standard deviations above the mean, and so Jack would be admitted. Okay. So this is kind of a nice application of z-scores besides just using the empirical rule. When we have populations, we can also use the z-scores to compare values from two totally different normal distributions. Now, what if we're not normal? And I mean in the sense that we don't have a normal distribution. Obviously, we're normal, right? Well, we said a lot of things are normal: standardized test scores, physiological measurements, deviations from manufacturers' claims, right? But there's a lot of data that's right skewed. So salaries are right skewed, prices of consumer goods, like in the Craigslist apartment data set we saw, or human performance. These tend to be skewed. Notice that the distribution's not symmetric, it's not normal. We can't use the empirical rule. We can't use the normal distribution calculator. So what do? Well, I'm going to present this, and you won't be tested on this this won't be on homework, but it's a nice little result. You could think of it as the empirical rule for skewed data. There's this result called Chebyshev's data. And it says the probability that you're within a given z-score of the mean is going to be 1 over 1 minus z squared. Okay. And it doesn't work unless you're two z-scores or more away, or actually more than one z-score away. Okay. And so the probability that you're more than a particular z-score away from the mean is going to be 1 over z squared or less. So for example, if I take a z-score of 2, the probability that a randomly chosen data value is within a z-score of 2 above or below the mean is going to be 75% using this rule. 3 standard deviations, if you use this rule, it's going to be 88.9%. Okay? And again, I'm not going to test you on this, but it's kind of nice to know how to use. Okay? And if you use this on the baseball salary data, which is a skewed distribution, okay, we'll find out that the probability that we have a z-score, that we're within 2 z-scores of the mean, okay, we find out that this is, again, going to be roughly 75%. So the probability that a randomly chosen person has a salary between 0 and 1,344 is at least 75%. And I'm not going to ask you to use this. It's just kind of a fun thing. Notice that Chebyshev's is kind of a really weak rule because it tells you the probability that you get a value within a certain z-score, but the probability can be that or higher. So Chebyshev's says at least 75% is within 2 standard deviations, and it turns out the actual value, if you do the calculation, is 95%. So Chebyshev's theorem is kind of weak, all right? It's very approximate. Okay, so we're going to use Chebyshev's to answer this last question, which is, who was the better home run hitter? So we talked way back in the introduction about comparing things that aren't equal. And we said sometimes people from different generations want to compare, a particular sports figure and from their generation and currently and ask which is better. And so we can ask who was the better home run hitter, Babe Ruth or Barry Bonds? Okay, there's Babe Ruth, there's Barry Bonds. You can tell just from the photograph they lived in different eras, but again, we can't compare them directly because they lived in totally different time periods. Okay, in fact, Babe Ruth died before Barry Bonds was even born. But what we can do is we can see how they compare relative to their peers. Okay, in other words, I can look at the year when they were most dominant, and I can ask who was the more dominant player in their era. And it turns out if you look at their sports records, Babe Ruth was the most dominant in 1920. That's when he had that 54 home runs. We've looked at that data set. He was a far outlier. And Barry Bonds, it turns out, was most dominant in 2001. And so what I'm going to do is I'm going to collect data on the number of home runs each player hit in 1920 and in, 2001. And you can get that data from ESPN. It's easy to get. And it's valid. We go ahead, we check it out, but there's nothing wrong with it. I'm going to go ahead and plot the distribution of home runs from each year. And to compare them, I'm going to make a side-by-side box plot. And we can see without running any statistical tests, okay, we can see that clearly Babe Ruth is much more dominant than Barry Bonds. Okay. Here's Babe Ruth. Notice at 54, the next closest player is way down here at 19. So Babe Ruth basically hits close to 3 times more home runs than the next closest person. Whereas Barry Bonds, he has more home runs, but again, the next closest player is a lot closer to Barry Bonds than for Babe Ruth. So Babe Ruth totally dominates. Now, we could compute z-scores, right? How many standard deviations was each player away from their peers? And to get the z-score, we're going to remove those individuals first, compute the mean and the standard deviations of the remaining players for each year, which we can do, of course, in StatCrunch. I won't bother to do it. And what we're going to find is this is the mean and the standard deviation for the home runs in each of those years. Okay. And you can see that the mean for the number of home runs is actually really low. It's around 1 in 1920, and it's only around 4 in 2001. Anyhow, if we use those values and we compute the z-scores, so Babe Ruth had 54 home runs, and if you compute the z-score for Babe Ruth using this mean and standard deviation, it's a whopping 19.8. It's close to 20 z-scores, okay, 20 standard deviations away from the mean. That's remarkable. That's unusual for almost any data set. So Babe Ruth definitely dominates. And if you use Chebyshev's rule, which I won't bother to go through, and you ask how likely are you to be 19.8 standard deviations away, it's only a 0.3% chance. Meanwhile, if we look at Barry Bonds, he had 73 home runs, and I compute his z-score using this mean and this standard deviation, it turns out that he has a large z-score. I mean, again, remember the empirical rule tells you that for symmetric distributions, and these aren't symmetric distributions, but we know that for symmetric distributions, almost all the data is within 3 standard deviations, okay? Well, this is a skewed distribution, but still a z-score of 8 is really large. But notice his z-score isn't even twice, I mean, is basically less than half of Babe Ruth's, okay? So Babe Ruth is clearly dominant. Again, if you use Chebyshev's theorem, it tells you that the likelihood that you can get a value 8.4 standard deviations away from the mean is less than 1.4%. And so you can clearly see that Babe Ruth is the more dominant, okay? But you can use Chebyshev's rule to kind of, support that also. So that's kind of a fun little exercise. And people do that with different types of athletes. For example, on an exam, I might give you athletes from a different sport and ask you to compare their z-score and find out which is more dominant. Notice if I did this with a sprinter, right? We would want the z-score to be really large but negative, right? We want the person to be really far away from the mean, but the value to be a lot smaller than the mean. So it would have a negative z-score. Okay, I hope you enjoyed this video. You're ready to do the homeworks now. You know everything you need to be able to do the computations and to answer the conceptual questions. Thanks for watching.